Hi Pre-Calc students, Mrs. Fellon here. I am starting lesson 1 of unit 5. We're talking about exponential functions and their behavior. All right, so first I wanted to kind of bring your attention to the front page of our notes where we have these 4 equations at the top. First thing says, which of the following are exponential functions? Circle all that apply. So what I want you to make sure that you understand, and one of the goals here is to understand what does an exponential function look like. So an exponential function is a function that has a base, we call it either a growth or decay factor, and it is raised to a power of x. So for example, this is an exponential function, and this is an exponential function. So it's a base, like 7, raised to a power of x, or 1/7 raised to the power of x. This is a polynomial function, which we did in a couple units ago, and this, of course, is a linear function. So again, kind of notice the similarities of just looking at the type of equation or the function and being able to identify the kind that it is. So I'm going to go through a series of questions just about, hopefully that some of this will just kind of jog your memory from Algebra 2. It says all of these functions are in the form y equals b to the x, where b is called the base. Note that there is one point included on the graphs of all 7 functions. So what I'm looking at here is if we look at the graphs of all these, notice where all of these graphs cross the y-axis. If you notice, you might notice that they all cross the y-axis at the point 0, 1. And so what we're looking at here is, so that point is the point 0, 1. When you have this equation, y equals b to the x, what this value is out in front is we call this our initial value. And basically that's kind of like where you're going to start your function. If there's no other transformations like shifting left or right or up and down, then this ends up being your y-intercept. But once you start shifting this left and right and up and down, then that's not going to be your y-intercept anymore, which is why I don't call it a y-intercept, I call it initial value. Because I want to kind of use the common term that we're going to use throughout the course of this whole unit. So basically this number, this multiplier out in front is what we call our initial value. And it's going to help us graph our function. All right, next it says 3 of these functions are increasing. We'll call them growth. What must the size of the base for the function be in order for it to be growth? Well, if we're increasing, notice this one is decreasing, 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 constant. And the last ones are increasing, increasing, and increasing. So if we look at all 3 of them that are increasing, so increasing, 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 notice our b value, especially in comparison to the ones that were decreasing, like, so decreasing, 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 our b value is greater than 1. So if it's constant, it's equal to 1. So that's just like 1 to the x. Doesn't matter what you raise 1 to whatever power. It's still going to be 1. 1 to the 29th power is still 1, just like 1 to the first power is 1. So anyway, back to this question, these equations, in order for this to be growth, b needs to be greater than 1. So that's how I can look at this equation and say, this one's growth, this one's decay. So we call this growth, we call this decay. So that's what the next question says. 3 of these functions are decreasing. Let's call them decay. What must the size of the function be? So it has to be less than 1, but the caveat here is that it has to be greater than 0. So we're not talking about negative bases, okay? The negative number that we're going to deal with is going to talk about a reflection when we talk about a negative in front. b may never be negative. Also, since the exponential functions must either grow or decay, there is another number not allowed in the base. So in other words, what I was getting at here is in order for this to be called an exponential function, b can never equal 1. Because if it equals 1, this is no longer exponential. Remember what I said, 1 to the 29th is the same as 1 to the first power. So you would get a linear equation or a constant equation. So if you notice in how we represent, growth, b is greater than 1, decay, b is less than 1 but greater than 0. Notice that neither of these have b is equal to 1, and that's because that never can happen. If it equals 1, then it's just a different type of function. Number 5, look at these 3 growth functions. What happens to the steepness as it goes from 2 to the x, 3 to the x, and 10 to the x? So in other words, as the base increases, what happens to the steepness? Well, pay attention to the steepness of the line. 2 to the x, 3 to the x, 10 to the x. The bigger the base, the steeper the line. So as the base increases, the line or the graph gets steeper. And then the decay function, has kind of the same scenario as it gets closer to 0. So we go from 1/10 to 1/3 to 1/2. It gets from, well, actually, if we go the other direction, 1/2 to 1/3 to 1/10. As 1/2, 1/3, 1/10, as that base gets closer to the number 0, see how kind of steep this line is getting? So if I had a number like 1/100, it would be a pretty steep graph. It's going to get closer to that y-axis. Question 7 says, all the functions in the form y equals b to the x, they have the same domain and range. For all exponentials, you're going to have the same domain. It's going to be negative infinity to infinity. And again, you need to have the negative infinity first because it's always lowest to highest. The range is going to depend on, we're going to have asymptotes in this function. And so the range is going to depend on where your asymptote is. And so once we start introducing shifts, like up and down and left and right, our range will start changing. But if you notice, all of these graphs kind of are all greater than 0. Let's kind of ignore this one since it's not exponential. But see how they all approach 0? But the graph itself is all above 0. So the range is from 0 to infinity. We are going to put a parenthesis around 0 because if you notice, none of these graphs actually hit 0. And the reason why that's happening is because there's an asymptote there. So we'll kind of discover that here as well. But there's an asymptote here on all of these functions, which means, if you remember from our unit we just finished with rationals, in this case, the function's never going to cross this asymptote. So on all of these, there's an asymptote there at 0. If you look at your function, just kind of as a side note, this is going to kind of be the equation that we're going to eventually get to when we start shifting left and right and up and down. This value here, this k value, is going to dictate where your asymptote is. So that's why in all of these functions, since none of them have a k value, like they're all plus 0, plus 0, plus 0, that's why my asymptote is always at 0 for these functions that I just gave you. All right, if x is a growth function, then the limit as x approaches negative infinity, h of x is equal to what? And the limit as x approaches positive infinity, h of x is approaching what? So let's just look at our growth functions, because that's what we're asking about here. So if our growth functions, we're looking at what happens at the ends of our graph. So here's our growth functions. As x gets smaller, what do you notice about my graph? On all three of these, as x gets smaller, so on the left side of my function, my graph is getting closer to 0. And so I'm going to change this from an equal sign to an arrow. I don't like the equal sign. It's approaching 0. And the reason why it's approaching 0 is because it's approaching that asymptote. As x gets bigger, notice as x gets bigger, x gets bigger, x gets bigger. That's the right side of our function. Our function's kind of increasing without bound. In other words, it's going towards infinity. So again, change that to an arrow instead of an equal sign. Let's look at what happens at the extremes with the end behavior of our decay functions. So you're going to see opposite behavior. As x gets smaller, the left side of my function, my graph is going towards infinity. As x gets smaller, my graph is going towards infinity. As x gets bigger, my graph is going towards 0, or that asymptote. So it's pretty much the opposite. So here, it's going towards infinity, and as x is approaching on the right side, as x approaches infinity, my function's approaching 0. And again, it approaches 0 here because that's my asymptote. If your asymptote was something else, then it would approach that value. All right, let's do a couple other little things here and talk about a little bit more about some of the functions. Maybe you learned this from Algebra 2 as well. Which of these functions are equal to each other? So I'm just trying to get an idea of like recognizing what the negative exponent does. So if you remember from Algebra 2, a negative exponent means that to make the exponent positive, you take the reciprocal. So b of x, 5 to the negative x, is really the same equation as 1 over 5 to the x. So I take the reciprocal of 5 and make it positive. Likewise, so like this one, d of x, if I took the reciprocal of 1/5, I would get 5 to the x. So I wanted you to kind of match up the fact that these two are actually the same exact function, and these two are the same exact function. They're just written with negative exponents. So 5 to the x and 1/5 to the negative x is really the same thing. And 5 to the negative x and 1/5 to the x is really the same thing. All right, so let's look at growth versus decay or not exponential. So 0.3 to the x. What I would probably have you do here, if you don't mind, pause the video, answer these questions, just put growth, decay, or neither, and let's see how you do on this, kind of on your own. So if you did what I asked, you pause the video, you answer these questions, let's check your work. Because this is an exponential, the x is in the exponent, but this b value is less than 1, this is decay. On this one, it's still exponential because there's an x in the exponent, but this time the b value is greater than 1, so it's growth. Remember what I said about the negative exponents. What I would do is I would change this into a positive exponent. So I would rewrite this as 1/3 to the x. And so now we know that it's exponential because it's raised to the x, but my growth, or that b value, is less than 1, so it's decay. We can never have a b value that's negative. So in this one, so that's kind of a trick question, right? It's not, in order for it to be growth versus decay, or any of them, in order for it to be growth or decay, b has to be greater than 0. And so clearly this one's not greater than 0, so this is not exponential. This one, it's exponential because it's raised to the x, but my b value is less than 1, so it's decay. 7/3 raised to the x, it's raised to the x, so it's exponential, but the 7/3 is bigger than 1, so it's growth. This is x cubed, which basically means it's not exponential because there's no x in the exponent. This is actually a polynomial. So not exponential. And then we talked about this one. This would give me a constant graph, right? So 1 to any power. So this one would be not exponential. All right, we're going to go through one last problem, and I just want to go over one example of graphing a rational function, and then when when I see you in class, we are going to go over the rest. So I thought we'd do one together on the video, hoping that you can kind of get a head start on this. So a sketch graph showing the set of solutions to the function include at least 5 points. So when we graph 5 points, I'm going to have you make a table. Okay. The first thing that I'm going to have you graph is going to be the vertex of our function. And so remember when we talked about like the h and k and all that kind of stuff. So I'm going to have this kind of rewrite my equation. And the first point I want you to graph is the point h comma k. So in my equation here, my h value, remember we take the opposite of this, so my h value is 1, my k value is -6. So 1 and -6. I'm going to kind of put it here as one of my points. That's going to be your kind of your starting value. So 1 and -6. One of the other things I like to do when I'm graphing this, so you can just start plugging in values for x. So we did the vertex, and then you can start plugging in like, okay, what if x was 0? What if x is 2? What if x is 3? What if x is 4? And that's another way to build your table. I'm going to show you another way to graph this. So in addition to kind of just knowing that that's your vertex point because it's your h and k, a lot of times what I do is I start by kind of graphing my initial value. So if you remember, this a value out in front is called our initial value. So what I do, and I'm sure I do it different than other teachers, but what I do is I graph that point, but I'm going to use a pencil, and I'm going to, so initial value is 2, and I'm going to put an x at that point. Because what's going to happen is I'm going to shift that point. I'm going to eventually shift that point because I have the h and the k and everything going on here. So I start up here at 2, and then I'm going to apply my shifts. So remember, the h causes you to go right or left. and the k causes you to go up or down, right? So in my function, I'm going to the right 1 and down 6. So right 1, down 6. Okay, so I think I messed up on that one. We're going to go ahead and, I think I messed up on that h and k. So go ahead and erase that one for me for a second. I was thinking of it differently. So we're going to start with our initial value, which is 2, and then we're going to shift our function, right 1 and down 6. So 1, 2, 3, 4, 5, 6. So actually this point, so that would have been your vertex, or your h and k, if we didn't have any shifts. Like if we didn't have anything else going on in our function, like this 2 out in front and so forth. So I apologize for kind of messing that part up. But anyway, the point here that I'm looking at is the point 1 and then 1, 2, 3, 4. So it's actually 1 and then -4. So I messed that up because of the shift. All right, once you have this one, let's graph your asymptote. Remember when I told you that on the previous page, this k value is always going to be your asymptote. It's a horizontal line. Your asymptote is never going to be vertical for exponentials. So whatever this value is, so in this case, it's -6, that's where your asymptote is. 1, 2, 3, 4, 5, 6. So my asymptote is a horizontal line at -6. So step 1, I'm going to plot my initial value, which is your A value. Step 2, I'm going to shift your A value using your H and K. Okay. Step 3, you're going to draw in your asymptote. And so remember, your asymptote is your k value in your equation. And then the last thing is you're going to plot in other points. And you're going to be using what I'm going to call as like growth versus decay. In other words, you should if your graph is increasing or decreasing based on that b value, right? We know from this equation here that the b value is the number being raised to x, right? So this graph should be increasing from left to right. So it should be kind of approaching this asymptote, but increasing. So I might pick some other values like 0 and plug it into my equation. And if I get 3 to the 0 minus 1, that would be 3 to the -1, which is 1/3. 1/3 times 2 is 2/3. And 2/3 minus 6 is like -5 1/3. Now, if you wanted to use a calculator on that, I wouldn't blame you. But anyways, if I said -5 1/3, so 1, 2, 3, 4, 5 and 1/3, about right here. So what I'm getting at is I'm kind of drawing in this curve of my graph. We know it's approaching that asymptote. So pick some other numbers, like 2. If I plug in 2, I get 3 to the first power, which is 3. Do the multiplication next. Times 2 is 6. 6 minus 6 is 0. So now my next point is way up here, so it's going to get pretty steep. I wanted 5 points, so now pick 3. 3 minus 1 is 2. 3 to the second power is 9. 9 times 2 is 18. And 18 minus 6 is 13. 18 minus 6, yeah. So we're going to be off my grid here. We're going to be kind of like way up here. So there's a difference between finding points and graphing points. So I asked you to find 5 points. I don't expect you to have all 5 of those graphed. But let's find another point. So 4 minus 1 is 3. 3 to the third power is 27. 27 times 2 is 54. And 54 minus 6 is 48. So this is going to grow pretty quickly. So that's going to be hard to graph all of those points. All right, let's answer the rest of the questions. Write the end behavior of your function in limit notation. So as x gets smaller, my function's going where? Well, it's getting closer to that asymptote. So we're going to say it's approaching and then -6 in this because it's approaching our asymptote. As x gets bigger, my function's going off to infinity. So it's approaching infinity. State the domain and range. Remember what I said about the domain. The domain's always going to be negative infinity to infinity. It's always going to be all real numbers. Your range will depend on where your asymptote is. So basically, it's wherever it's everything above your asymptote. So if my asymptote's at -6, -6 to infinity. Just make sure you're using a parenthesis there, not a bracket, because you don't want to include -6 because that's an asymptote. Circle the x-intercept. Well, the x-intercept is right here, right? That's where it hits the x-axis. So that's the point 2, 0. Show that this point is a solution of the function by setting f of x equal to 0 and solving. So in other words, taking this function and making f of x 0. So 0 equals 2 times 3 to the x minus 1 minus 6. So here's how you would solve this. We're going to do a lot more of solving, so kind of keep this in mind. This is definitely very preliminary, but you might remember this from Algebra 2. First thing I would do is I would add 6 to both sides. Next thing I would do is get rid of this 2, so divide both sides by 2. So basically what you want, and so this is how we're going to solve it right now because I haven't really showed you how to do logs yet, but we know that this is 3 to the first power because any number is raised to a power, right? Sometimes we write it, sometimes we don't. But in order for this side of my equation to equal this side of my equation, I need this exponent to equal that exponent. So all I'm going to do over here is I'm going to say 1 has to equal x minus 1. Because in order for these two things to be equal, this exponent and this exponent have to be equal. So I'm going to add 1 to both sides, and I get x equal 2. So I solved this equation, and I got x equals 2. I graphed this equation, I found my x-intercept to be 2. When you come to class next, we're going to kind of go over a few more graphing problems, and then you guys practice on what we did in this section. All right, bye for now.